Friends, we discussed in the last lecture some aspects of electrolysis, and I emphasize the importance of limiting current density. And it arises, as I mentioned, very often out of a diffusion controlled process, where the diffusion of cations towards the cathode is slow compared to the discharge reactions at the surface. And when that happens, we have the concept of a limiting current, which means for a given area of the electrode, there is only this much of current we can pass. Not only limiting current, if you divide that by the area of the electrode, we have limiting current density. So, the electrode has a maximum metal deposition rate. This brings us to the question as to what we do then to increase the productivity of electrolytic cell. One obvious answer was to increase the area by increasing the width, not the depth of the electrode, and then beyond that have multiple cells. So, because in one given cell with a given electrode area, you cannot produce more than certain amount, you can always do that if you have many more cells. So, most electrolytic plants will have many cells. It is not like a pyrometallurgy, you have one reactor which produces a lot of metals. Here we will have many cells, often called pots, which are actually electrolytic reactors. After all, there is reaction taking place there. So, we will have many of them. Question is, how do you arrange them? Now, we have seen two basic things, that if you put all the electrolytic pots in a series, so the same current flows through, then the current level is low. So, the I square R loss in the electrical circuit will be low, but the voltages get added up. So, on the whole you are operating with a higher voltage from one end to the other. But there the disadvantage is, if one pot is in trouble, then the entire line is in trouble. You cannot repair one particular pot. You can eliminate this problem by putting all the pots in parallel, and then the current which comes gets split into the pots in parallel and then merges again and goes out. So, the current increases, but the voltage is low, because they are operating, all the pots are operating under the same voltage, which can be given from two bus bars. So, these are the two extremes. There the advantage is that your voltage requirement is low. You can take out any pot at a time if you need repair or whatever, but your current requirement is high. I square R loss will be high. For that, you have to provide for adequately thick electronic circuit, so that the electronic resistance is cut down and you do not waste energy in heat losses in the electronic circuit. Now, there are other ways we can think of doing things in practice. Look at this slide, for example. Here we show what we call a series parallel arrangement. Now, what is it that it means? Now, this is a collection of electrolytic cells. In this, there are number of cells. You have anode, cathode, anode, cathode, anode, cathode, anode, cathode. They are all in series. Here are also several cells in series. These are also several cells in this are in series. But look at these cells here, they are arranged in parallel. Why? Because you have an anode bus bar and a cathode bus bar. From the same cathode and anode, you are supplying this current to this cell, this cell, this cell, this cell. The same current is split into 4, and they again go, they are split into 4 and again split into 4. So, these are parallel arrangements put in series. Now, here what is happening? You have a cathode and anode which constitute a cell, then also you have a anode and cathode constitutes a cell, anode and cathode constitutes a cell, so it goes like that. So, we have a series parallel arrangement which has its own advantages. It is a compromise between parallel and series arrangement. This is another very interesting way sometimes electrolysis can be carried out. It is that there is a whole lot of electrodes put in like this. One side is anode area, this is cathode area, this is anode, cathode, anode, cathode, anode, cathode, anode. So, if we suspend in the electrolytic pot a number of electrodes like this, then metal will be deposited in these surfaces only. These are the cathodic surfaces, and the anodic reactions will take place here. Such cells are known as bipolar electrode cells, means an electrode is bipolar. On one side it is plus, on the other side it is minus. I will show you an application of this in a process that almost became successful for aluminum electrolysis. So, to summarize, when cells are in series, one passes the same current, but cell voltage adds up. When cells are in parallel, voltage is better, but current can be high. We can have what we have here, parallel series connection. We can have bipolar electrodes. These are various way of handling electrodes in a system. But now, let me come to a very interesting development, which is a semi-commercial step, and it is a very radical way of thinking. Some researchers argued that our problem is that an electrode surface is limited. So, in a given volume we have an electrode, current is limited. They said, why can't we think of a different kind of electrode which is not a planar solid electrode, and they came up with the idea of a fluidized bed electrode. Now, what is a fluidized bed electrode? For that, look at the slide. In a normal setup, what we have is an electrolyte, and here is a cathode, and here is an anode, and suppose it is an aqueous electrolysis where oxygen bubbles are coming, and here metal is getting deposited. In a fluidized bed setup, we separate the two chambers. The anode remains as it is, because it is a permeable diaphragm, a kind of membrane, the electrolyte permeates. But in this chamber we have a current feeder, then there is a diaphragm here through which electrolyte is pumped, and a whole lot of particles are fluidized. These are particles of the metal that are supposed to be deposited here. So, suppose metal M in this solution is to be deposited. We take powder of metal M, have them dispersed in a thick suspension, and that is fluidized. Means, if you leave the powders as it is, perhaps they will all come here and make a bed, but then the electrolyte has to be pumped through the bottom with a certain speed, so that they are thrown up and they are fluidized, they cover the entire area. Now, you might say, what is happening to the electrolyte you are constantly throwing up? It will come out this way. How? I will tell you. Now, what happens when you have a fluidized bed electrolyte? You have a current feeder stuck into an electrolyte where there are an infinite number of metal particles floating around. And at any instant, there will be innumerable number of particles in contact with the electrode surface, in contact with each other, and this chain now functions at the cathode surface. So, the cathode is no longer a planar surface, it is the surface of infinite number of fluidized particles of that metal, which are in motion, but at any instant many of them make a chain, many of them are in contact with the feeder, and the surfaces of all these particles provide a surface for electrodeposition. Now, look at this beautiful concept. You no longer have a plain surface on which metal is deposited. The metal now can deposit on a much larger surface, the surface area provided by the surfaces of these fine particles. Now, it has been found by actual practice that if it is done properly, you can increase the limiting current by an order of magnitude, means 10 times, which means compared to a plain electrode, when you have these fluidized bed particles providing the surface for electrodeposition, the available surface area is more than 10 times. What does it mean? It means in the same cell, same size, almost the same arrangement, excepting that instead of having a flat electrode surface, if you provided a mass of particles in a fluidized bed, we can now bring in 10 times more current to the cathode surface, and therefore, productivity can be 10 times more. Now, where is this metal going to be deposited? It is not on that surface. The surface is not there. There is no planar surface for deposition. What we had initially an electrode surface, here it is only a current feeder, maybe a sheet of the metal, maybe a rod of the metal. The metal is primarily being deposited on the particles that are in the fluidized state, which means if you provide a seed means certain number of particles, they begin to grow, because on them metal is being deposited, and they are not static, means the particles which are in contact with the feeder or in contact with each other are changing constantly. So, means a certain n number of particles were in contact with the feeder, in contact with each other, metal deposits on them, and then they run away, fresh particles come. So, the overall effect of this is the particles continue to grow. So, you bring in the seeds continue to grow, and because there is a continuous flow of electrolyte from the bottom for fluidization, these particles and the electrolyte will flow out of here, and you must have a screen to take out certain fraction of particles. So, you bring in more and more seeds. So, by adding certain amount of smaller size particles, you get larger size particles. You can do something more also. In this, you can take a different kind of metal particles, fluidize them, and have them coated with the metal that is being deposited. You can do that also. Normally, you would need that. You are interested in producing a certain metal from the electrolyte. So, you take the same metal particles, fine particles, have them fluidized, and on those particles fresh deposition takes place. So, each particles increase a bit in diameter, and since there is a continuous flow, they are discharged with electrolyte. So, it is a continuous process. You go on feeding finer metal particles, they become slightly coarser, you take them out. Product now is not a layer on a planar surface. No, the product is a powder, a fine powder, which is coarser than the powder used in the fluidized bed. Now, sometimes it can be an advantage. You might like to have the metal in a particulate form in powders. It can go directly for powder metallurgy. It can have other applications. So, this is the principle of fluidized bed electrolysis. So, I will repeat this. In this, the cathode is made up of fluidized particles of the metal being deposited. The current feeder may be a steel rod or the same metal. It can be a sheet also. Electrical contact is ensured by innumerable particles that are in contact with the feeder at any given time and with each other. Deposition is on powder particles that are continuously changing, fresh particles replacing the old. We produce bigger particles that are continuously removed, typically limiting current density increases by 1 order of magnitude compared to the conventional cell. Now, in principle this is very good. What are the disadvantages? There will be disadvantages. Firstly, that you are not getting a consolidated metal layer on a plane surface. Secondly, you end up with powders which you may or may not want. If you want it, it is fine. Secondly, you are now do not have a static system. You are continuously pumping something, you are fluidizing. So, that brings in more plumbing, that brings in requirements of handling the discharge, separating the coarser particles, constantly bringing in fresh finer particles, etcetera, etcetera. Although this has been proved to be very effective, not many industries actually operate on this principle, because we will find again and again that when you do R&D, we come up with exciting findings. Exciting findings, but the problem comes technologically they are not very easy to adopt. That is where we should know the differences at step. You know, what is research? Research is there is a phenomenon you want to study. When you do R&D development, that research has a goal, you are doing it for a particular purpose. Now, here fluidization would be a research topic, how it is fluidized, what should the particle size, etcetera, etcetera. If we want to make a fluidized bed setup to study this phenomenon, whether it can be applied in an electrolytic cell, it becomes R&D. But then technology is not R&D. Technology asks two other questions. Are they technologically feasible? Are there methods of fluidization? Is there a suitable feeder material? Will it apply on a large scale? These questions are questions of technology. Suppose technology is also satisfied. To be a commercial process, then there are some additional requirements, and there will be, are there economic advantages. So, from research to R&D to technology, then a commercial process cannot be there unless there are questions of profit answered properly. Will it compete with another standard process and be more profitable? Okay, it is giving you 10% more productivity in one cell. At what cost? The industry may say, why bother about it? I would rather have 10 different cells and get the same result without changing anything that I have. So, the question of economic profitability comes in. That is why after R&D we do what we call techno-economic analysis, TEFR, technical feasibilities and economic criteria. Now, even if you have satisfied all the criteria of technology and commercial process, it may not be an actual process in operation, because then there are other questions. You have answered the questions of technical scientific feasibility, technical feasibility and economic feasibility. Then there are other questions. Questions like, do they conform with environmental regulations? Will they satisfy socio-economic conditions, labor requirements, many government laws, regulations. So, there are many things. So, we may develop something in a laboratory, but very often it goes up to a technology, then stops, or it can go to a commercial step, but it may not be an industry. Anyway, I am digressing. What I am saying is an exciting idea. There are many such exciting ideas in non-ferrous metallurgy. Some have gone all the way to become a viable commercial process, but many have not gone the full distance, and you should always know why they haven't gone the full distance. That is the reason why this aluminum electrolytic cell that we will discuss, which is about 100 years old, still basically remain in principle what it was 100 years ago. Blast furnace process, for example, is 400 years old, still operates the way it operated 400 years. There have been many refinements, but that does not mean we give up, because when you come to the modern developments, when you talk about nuclear metallurgy, nuclear metals, all these have come because you understood the theory and there was a lot of R&D. Now, coming back to this question of fluidized bed electrolysis, in theory it can produce 10 times as much in the same cell, but there are technological problems. The problem of handling large volumes, you need pumps which will continuously pump things, the pumps may fail, you need more plumbing, you need if you have seen a fluidized bed setup, there are some very interesting requirements of fluidization they have to satisfy. Anyway, let us move ahead. Now, so far we have been discussing electrolytic reactions where it is diffusion that controls the whole thing, because the diffusion is slow, discharge reaction of the surface is fast. And that is what I have said here, that metal deposition reactions are usually controlled by slow mass transport and hence involve negligible concentration over potential. When discharge reaction, that is M n plus to M plus N E, is slow, then there can be activation over potential. Now, there are situations where the process is not diffusion controlled, means it is not because of a gradient that the metal ions are coming to the surface and that is defining the steps. Actually, this step is very fast, that metal ions going to the surface is not a problem. It is at the surface that discharge is slow. There are not many examples of this, but there are some, and this is what gives rise to activation over potential. This happens in the case of discharge of hydrogen in aqueous solutions, because this can have significant activation over potential. Now, here let me stop for a moment and tell you that this is a very interesting exception, which is a very happy exception. There are many such happy exceptions in the world. One I suddenly thought of is the example of ice. You know, ice floats on water. If you have not thought about it, think about it. This is an exceptional thing that nature has done, because most solids, when they melt, they occupy more volume, because after all, why does a solute melt? Now, one simple theory to explain the phenomenon of melting is that you have a crystal lattice. Now, in the lattice you bring in some empty spaces like holes, so that the volume increases and the lattice is no longer rigid. So, it becomes fluid, it becomes a liquid. So, in most cases the liquid occupies more volume than ice, which means more volume than a solid, which means solid always has more density than the liquid. And if you melt many metals, you will find the metal melts and the liquid is on top, metal is solid is at the bottom, because it is heavier. In the case of ice, because of a strange phenomenon, ice becomes lighter. It is a very rare exception. There are 1 or 2 metals that happens. Again, let me repeat, most solids are denser than liquids. Ice is an exception, it is lighter. So, what happens when ice melts? It floats. Of course, it floats also, so that only a fraction is above liquid, 9/10 is below liquid, but this is vital. In the Arctic areas in winter, when everything is covered by ice, there is water below the ice, because ice is floating, and because there is that water, the Arctic life exists. Fishes do not die. Had ice been heavier than water, ice will form, go on sinking, water will be on top, it will go on freezing, everything, all animal life will die. So, the God has created that exception, that ice will float with most of it below the surface, but below that water will remain, and ice is also an excellent insulator. So, once it floats the top, it will not allow the heat to go in, the fishes can survive under the water. It is a very happy exception. In metallurgy, you have a very happy exception, and this exception happens in the case of hydrogen evolution. Now, when we have an aqueous solution electrolysis and we are evolving hydrogen, then a very interesting phenomenon takes place. Because the hydrogen atom is very small, its diffusion is very fast through the aqueous electrolytic media. Ion will diffuse very fast, it will go to the cathode. It is the discharge of that hydrogen ions on the hydrogen electrode that is slow. So, there will be an accumulation of hydrogen ions, because it is coming very fast, it is accumulating. So, that hydrogen gas, hydrogen potential is going to change, is going to increase. See the implications of that, but before that let me read the slide. When discharge reaction metal plus Ne is slow, there can be an activation over potential. Discharge of hydrogen in aqueous solutions, here put hydrogen in place of M, there can be activation over potential, which means discharge of hydrogen in aqueous solutions changes the hydrogen potential. Now, let me stop for a moment. In aqueous electrolysis, anode is generally made up of inert lead, antimony, arsenic alloy. Anodic reaction primarily involves evolution of oxygen. In acidic solution, what happens? Water is being dissociated to produce oxygen and hydrogen ions. In alkaline solutions, we are producing alkali dissociates, gives oxygen, water, and acidic solutions therefore become more acidic, and alkaline solutions become less alkaline. So, in acid leaching processes, that is an advantage. Acid leaching processes followed by electrolysis in theory consumes no acid, because you have consumed acid, produced an electrolyte, electrolyze, you generate acid, it goes back. Now, suppose you have a solution of zinc salts in an aqueous solution. You are trying to electrolyze zinc. Now, go back to the electrode EMF series, Electromotive force series. Remember, Electromotive force series is where we showed which metals are active, which metals are not active, and I will show you the series once again. I have it here. Electromotive force series. Okay. Now, here, right in the very beginning, if you can look at what we have it here. Remember, in the very beginning of my course, I had said that all metals can be arranged in terms of reactivity, and one common way would be in terms of electrode potential in aqueous solutions. In electrode potential series, we had some very highly reactive metals like cesium, lithium, potassium, calcium, sodium, magnesium, titanium, aluminum, etc., where there was no question of getting them from electrolysis of aqueous solutions, because they are so reactive. The moment they are produced, they will react with water and displace hydrogen, because hydrogen comes below them. Now, on the other hand, below hydrogen we have noble metals, copper, silver, platinum, gold, etc. Always you can electrolyze in aqueous solutions and they will come out, because they do not react with hydrogen. Problem is in places which are close to hydrogen, this series has been drawn with hydrogen potential as 0, H1 potential as 0, and slightly above them is zinc, chromium, manganese, up to manganese. Now, normally you should say that you can never produce these metals by electrolysis of aqueous solutions, because they should react with acid and produce hydrogen, and this would happen if you have a mild acid solution. If you put zinc in that, zinc will dissolve, hydrogen will come out. If you put manganese or chromium, same thing should happen, because they are more electropositive than hydrogen. But the situation changes during electrolysis, and it can change only up to manganese. Metals up to manganese can be produced by electrolysis of aqueous solutions, because of this exception that hydrogen gives rise to activation over potential. If we plot the situation schematically, we have three situations. I am plotting here the change in electrode potential with respect to current or current density, whatever. Now, the more current you pass, the more there is a change in the electrode potential. Why? Because when you are passing current, more and more hydrogen is coming, and hydrogen gas and hydrogen ion potential will increase. Metal ion potential, if you compare, will also increase, but in the case of noble metals, this is always higher than this. So, noble metals can always be deposited, no matter what is the current you are passing. On the other hand, if you go to the other extreme, very reactive metals, like as I said, cesium, sodium, potassium, etc., they are also, with increase in current density, electrode potential will change for both these hydrogen ion and metal ion, but there is no chance that you can go to high enough I to make metal ion potential higher than hydrogen ion potential. However, in the case of these intermediate metals, as I said, going up to manganese and zinc and manganese, there is a crossover. Means if you increase I, hydrogen ion potential can change like this, metal ion potential can change like this, but beyond a certain value of I, hydrogen ion potential is more. So, metal can be deposited at the cost of hydrogen. Means normally if you are putting zinc in an acid solution, hydrogen will evolve, but when current is passing, because of this phenomenon, hydrogen will not evolve and metal will deposit. This is the basis of zinc metallurgy, that we will see that zinc can be produced from aqueous solutions, even though in the electromotive force series it is more electropositive than hydrogen. Now, let me summarize what I have said this far before I proceed. In any electrolytic cell, the energy required would be voltage into current. If cells are in series, voltage is more, same current is flowing through, current is less. If they are in parallel, current has to be split up, current is more, voltage comes from the same bus bars, so voltage is low. Overall energy will be the same. In the industry, technology is determined and it will be somewhere in between. You can have series parallel, but emphasis would be in parallel, so that you can remove any pot at any time you like. No matter what you do, our aim will be to maximize current efficiency, because we do not want the current to go for anything other than metal deposition, except in the case of high temperature electrolysis, there the current also has to provide heat, because after all you will not heat a pot from outside. The current itself will generate heat. So, that will come from the resistance of the electrolyte. So, that voltage drop we have to account for, that is advantageously used, but we would not like energy losses in the electronic circuit or in the electrodes or at their joints, etc., etc. Those are wastages. We not only want current efficiency to be maximized, we also want voltage losses not desired to be minimized, and we want energy efficiency also maximized. I will come to this energy efficiency theoretically. The theoretical decomposition, that is the sum of cathode and anode voltage, can be minimized by manipulating anode reaction. Now, let me explain this. Essentially, the voltage requirement for any electrolytic cell, as I have discussed earlier, has many components. First is you need a voltage to decompose the solute. Then you have voltage to overcome overpotentials. Then you need a voltage to overcome the resistance of the electrolyte. Then you need voltage to overcome the resistance in the electronic circuit. Then you need some voltage to overcome the resistance in the electrodes, of which the resistance of the electrodes, resistance in the electronic circuit, they must be minimized, because they only heat up the joints, electrodes or the circuit. For aqueous solutions, yes, we can minimize the resistance of the electrolyte. For that, we can bring the electrodes very close together. Over potential, there is not much we can do. It can arise out of if it is a diffusion control process through concentration over potential, or if in the case of hydrogen discharge, it can come from activation over potential. But now examine the basic thing is you need a potential to break this solute. Now, suppose the solute is M x. M gives you the cation N plus, which goes to the cathode, x gives an anion which gets discharged at the anode. We are really interested in metal deposition. This reaction can be of many kinds. We can manipulate the anode reactions. Why should we manipulate? Because the total voltage that we require for deposition or breakage up would be sum of this potential, metal ion potential, and the anodic potential. Now, the cathodic potential nothing you can do, metal ion to metal you have to deposit, but here there can be different kinds of reactions, and that can change the requirement of metal deposition from its solute. Consider an example. Suppose we find a solute in which we electrolyze, we will come to this in the next lectures, Al2O3. We have found a solvent. We will have to break it to bring aluminum and oxygen. We have to find here a cathode on which aluminum will get discharged, produce aluminum. Here we can think of an electrode, anode. In theory there can be a platinum where oxygen will evolve. So, you are breaking aluminum into aluminum and oxygen. This is the cathode reaction. This is the anode reaction. There is a potential here required, a potential here this, and the total potential, decomposition potential would be cathodic potential plus anodic potential. Can we lower this? If we can lower this, we can lower E. And no harm done. You are metal deposited, you lower this. Can you do this? Actually, it happens in the case of aluminum electrolysis. What you do here, we do not have a platinum, we have a graphite electrode. So, when oxygen comes here, it reacts to produce CO and CO2. So, the reaction is not oxygen ions giving you oxygen gas, it is oxygen ions coming reacting with carbon to produce CO2 gases. So, it is a totally different anode reaction, and actually it brings down the voltage requirement. Why should it bring down? Because by this reaction you are efficiently eliminating oxygen ions, you are consuming them. Means you look at it this way, that you have produced oxygen, that oxygen has reacted with CO2 to produce more stable compound. So, you require in theory a lesser amount of energy. Now, many attempts have been made to play around with anode reaction, so that the total voltage requirement is low. Unfortunately, most these efforts have not been successful. When we come to discussing actual examples, we will see that. Okay? So, now I am coming with this to the conclusion of module 4. Now, I would lead you to module 5, from where we will start discussing extraction and refining of specific metals. Now, there is, I can see a potential problem there, because I will have to give you a lot of facts, and many of these facts have evolved out of centuries of practice. Like I told you right in the beginning, zinc, lead, copper, they have been produced for hundreds if not thousands of years, and many things have evolved. I do not know how they have evolved, because without knowing the theory, they have come up with excellent findings, and still many people do not understand how they found out those things. but many of the things that were done in the past still continue because they are found to be theoretically sound today. And it is like those Ayurvedic medicines. So many things have been found today that what is written in our Ayurvedic textbooks 2000 years ago, treatment of various diseases using various medicinal plants, they are actually valid. And like the Chabban Pras, for example, its main ingredient is amla. It has been going on for many centuries, but today it is proven that amla is one of the richest source of vitamin C, and it is very important, vitamin C, and it is one of the richest sources. How they found out? They found out basically by trial and error. Now, so far when it comes to these medicinal things, they say there is a difference between experimental research and experiential research, that you do not do experiments to prove this or prove that, you experience. Like yoga, yoga benefits are well established. You cannot prove that by experiments. You cannot say do 3 days, 3 hours and after 1 week make measurements, no. But experience over generations have shown certain things to be right, certain things to be wrong. In the case of technological developments, there have been experiments and there have been experiences based on which many things have been evolved. They have been proved to be very right. Now, so I will give you a lot of facts that do this, then do this, then do that, and this. They will give you many flow sheets. I do not expect you to remember these facts. I do not expect you to remember these flow sheets, because they are in the literature. If you ever want to know what is done, you can always go and refer to a book. And I am again telling you, the book now you will have to read is this book of mine called Extraction of Non-Ferrous Metals by H.S. Ray, R. Sridhar and K.P. Abraham. It has been published by Affiliated East and West Press Limited many years ago, 84 first published. It gets repeated every year. But I am going to follow this book and also some material I am collecting from here and there. But there are many things in this book I cannot discuss. For example, there are flow sheets after flow sheets and data and facts, and I won't go through all this. What will I do then? I will try to give you facts and discuss the whys of these facts. If this is done after this, why this is done? If something is not done, why it is not done? So, when I go for discussions of individual metals, please try to follow my discussions on whys and why nots. I need to give you some facts, I need to give you some flow sheets, some data, because after all they have to go on the record. And someday you might like to know, okay, what is to be done there, the thing should be available. Then when you do that, you will also know why you do that. But again I am saying, I do not expect you to know remember the flow sheets, remember the facts. I will not emphasize the flow sheets, I will have to show them, but I will try to emphasize why something is done. And some two similar things, why similar approach is not available. Now, I will put a lot of emphasis on aluminum, because after steel, aluminum is going to be a backbone of our industry, and aluminum is very important as a metal. And discussions of aluminum, for that you will have, I will again refer to two books. One book is on molten salts, slags and glasses, again authored by me. It has been published by Allied Publishers Private Limited, New Delhi, a few years ago. Another book to which I am going to refer and from which I am going to take a lot of materials will be on this book, Energy in Minerals and Metallurgical Industries by H.S. Ray and others. It is also published by Allied Publishers Limited, New Delhi. I will suggest that you should buy this book, because if you want to be a metallurgist, this book will be very useful to you. I would also suggest that if you have interest in non-ferrous metallurgy, you can certainly buy the book on non-ferrous metals. The book on fused salts, slags and glasses is slightly at an advanced level. This is a reference book, but you should try to refer it to this book, especially when I start discussing aluminum. Now, let me introduce you to what I am going to do in the next module, module 5, because I have to relate whatever I have done so far to that part. Now, in the module 5 will be about production of metals from oxides. Now, again let me take you back to the lectures I delivered some time ago. I had said we are going to approach production of metals in this course not alphabetically, not starting with aluminum and ending with zinc. No, we will proceed according to the sources from which they are coming, and it so happens some metals come from oxide sources, some we get from sulfidic sources, sulfides. Some are produced from halides, they may be natural halides or there may be halide intermediates that have come from oxides or sulfides, but basically we start with the halides. Lastly, we will discuss metals which are noble metals, which are in nature not as compound, but in free state. And lastly, we will discuss production of secondary metals, metals from secondary sources, means wastes. These are the 5 categories. Now, we will start the next module with metals from oxides. It does not mean that they would all follow the same flow sheet and same method. No, you can have a metal A as an oxide and metal B as an oxide. It is quite possible they will not be produced by the same method, but you should know why they are not produced by the same method. It is also possible that many of them would be amenable to the same method. So, we will try to understand the logic of the similarities and differences. Thank you, and then I will start the next lecture starting with metals from oxides. Thanks.